Welcome back. It's a pleasure to introduce our next speaker, who is going to be online, so in a post-COVID online world, that's obviously acceptable now. So Simon Scheidegger is an assistant professor in economics at the Faculty of Business and Economics at the University of Lausanne. And his research is focusing on numerical methods to solve and estimate high-dimensional optimal control problems and then to apply them to questions in climate change, microeconomics, and finance. So I'll hand over to Simon. I hope you can hear us. Well, we can't see him. Anyway, we're looking forward to your talk.
Thank you so much for having me. Thanks to organizers for inviting me. I would have loved to come in person, in particular, since I lived in Canberra some 20 years ago. Would have been nice to see how things changed. But since the entire family relocated from the United States to Switzerland last week, it was a bit of a hustle. So I hope you take my apologies here. Anyway, now let's talk about computational economics and applications in climate change. So this is a big strand of my research and some of my colleagues. And so I have to mention that this is sponsored generously by the Swiss National Science Foundation. I know in the room there is a lot of climate scientists. I don't need to convince any one of you that, of course, climate change is a thing, right? So we have an increased frequency of all sorts of disasters, more floods, hurricanes, wildfires, etc., etc., etc. So this bears, of course, a lot of human suffering, but it also affects, mankind in terms of, in economic terms, right? So all those things have a price tag. And moreover, of course, climate change impacts different people with different age in different regions of the world differently. So we have, a lot of heterogeneity, who is impacted how on this globe by climate change. So climate change not only has this tragic component, but of course it also has a political component. So people in Europe start to glue themselves to the streets to protest. There's this famous speech of Greta Thunberg at the United Nations, start to be, quite outspoken, among others. So we are scientists, and we want to do something about climate change, but we want to do it in a sort of principled way, without the protest for the time being. One of the ways to tackle climate change is carbon taxation. And carbon taxation, means you need to attach a price to, how much a ton of CO2 costs, like how much harm is it doing to the environment. Now, how can we compute such a price? And the price for CO2 emissions is computed with so-called integrated assessment models. Integrated assessment models, these are models that marry economic models with climate models. And of course, as we will see in a moment, we cannot, of course, not afford to run a fully fledged climate model, but we need to have some sort of reduced form type of models. And therefore, the integrated, it's actually, do you see that I'm clicking around, or is it always the same picture on your display? Well, anyway, I'll move on. But hello? Okay, now it changes. Sorry. So these integrated assessment models, they're subject to a lot of uncertainty, parametric uncertainty, model uncertainty, and then all sorts of climate-related uncertainties. And they're numerically quite hard to solve because they have a lot of uncertainty in there, of course. So that means you need to compute high-dimensional expectations, but they're also, the functions, the optimal policies that we want to find out, they're highly nonlinear and make the life miserable. Now, just for those of you who are not so much familiar with economics, just one quick slide. What people use in terms of carbon tax is typically also referred to the social cost of carbon. The social cost of carbon is loosely speaking the cost that is caused by an extra ton of carbon emitted on top of a background scenario. So you could imagine, like if I emit an extra ton of carbon, it will trigger a fraction of a flood somewhere that will cause some economic cost. And this is the social cost of carbon that we want to be able to compute. Now, to set up these integrated assessment models, so those models that marry physics with economics, we of course would like to have these models specified as rich as possible, which is not clearly not possible, but like still we would like to have as much state-of-the-art climate science in such a model. We would like to have the best possible economics model. And at the same time, also we want to have a time to solution which is not years, but rather minutes or hours on a supercomputer, and such that we can run parameter studies and try to study the sensitivities of the policies, etc., etc., etc. So the endeavor and also the team that we're working on that problem is super interdisciplinary. We have climate science on board, we have applied math on board, and also computational science on board. So this all goes to this magic cauldron to tackle this problem. So what we mainly do is we develop generic solution methods to solve these problems. So I put here 2 GitHub links that you from our recent developments that you can download, such that people in the community that have particular policy questions in the field of climate change economics can actually study, whatever they're interested in. So our main goal is to deliver to the community generic tools. Now, so what I will talk about is for a moment, like the basic ingredients of the models that we try to tackle a bit more formally. And then in particular, I will spend focus on how contemporary computational tools from the computational science literature, and then namely deep learning, and also contemporary hardware, namely massively parallel GPU clusters, can help us to solve those problems in a short amount of time. And then, if time permits, I give you few example results, such that you get an impression, what these models spit out. Now coming to the climate input of our models. Of course, as you all know, the Earth's climate is an energy balance type of problem. If there's more input than energy output, we have climate change. This is due to greenhouse gases that hold back some of the energy. Now, of course, what we would like to have is, climate in our econ models as well as possible. But the models that you climate scientists work with, for us, that would be a function call that would take forever to solve the econ model. So we clearly cannot do that. So what is done in climate economics, we need to take a very simple approach, and already this one is quite costly. So typically we rely on emulators to model the climate. Most of the time we're using the so-called DICE model that has is a 5-dimensional simplified model of climate. So it has 3 reservoirs for carbon. So it has a a lower ocean, a middle ocean, and the atmosphere. And so the carbon concentration moves as a linear system, where here you have the emissions that can come from economic, so human activity, and the exogenous sources like land enter here. That's 3 state variables, and the temperature, we have 2 state variables, also a linear system. You have the atmospheric temperature and you have the ocean temperature. Then via radiative forcing, this can change. So that's just 5 state variables to model the climate. Then how do you how does one then marry those climate models to economics? So this is how all these integrated assessment models roughly look like. You have an economic model to be defined abstractly. Say you have here a factory in this model. You emit CO2. I put here the plus minus sigma because like this process has some uncertainty around it. The emitted CO2 will affect climate. Temperature will go up, but also within, it has some uncertainty around it. This increased temperature will trigger some damages, more floods, wildfires, whatever. This will in turn again hit the economy, so destroy capital stock or whatever. So it has some cost attached to that, and this goes in circles. Now this looks simple, but it's quite hard. So for one reason for being hard is like there's a lot of uncertainty in those models. One simple source of uncertainty, which is like sort of the elephant in the room, is the damage function. So like with increased, here we have like a global damage function. So with an increased temperature, in a nonlinear way, capital is destroyed. But there may be tipping processes like melting of ice sheets, etc., etc., etc. So like some of those damage functions, they're fitted against historical data. They assume like a quadratic functional form, but there's others in studies that believe that this damage function can look something like t to the 6, and no one knows exactly where such an aggregate tipping point would take place. So this is just one source of uncertainty, and this is many more. Now, and I don't want to scare you with equations, but like I just want to show once, how then such a model looks like. So what we at the end of the day want to do is we want to solve an optimal control problem. So you have, for instance, here like a government, so a benevolent planner that wants to maximize the welfare of whatever welfare means, subject to a bunch of constraints. So this is a dynamic optimization problem. He can choose, next period's capital consumption or how much he would like to, dampen CO2 emissions. Subject to, so here this line is the so-called budget constraint, but essentially tells you, how much capital is used to produce goods, how much is saved. And now where is the climate coming in? So all these equations down here are the climate emulators constraints. This could be also, from another emulator, but these are the climate constraints. Here we have some economic processes. But here, on this first constraint, what is interesting, you have here this omega. This is a damage function as a function of the temperature and the tipping points. So that means with an increased temperature, you would essentially kill some of the capital, reduce that. And this first term is mitigation. So like you can, to prevent some emission, you have some policy instruments to avoid emissions, say taxes, etc. So this is the most simple stochastic integrated assessment model you can think of. this looks so simple, but this was only recently solved in a study. And to solve that, people used like hundreds of thousands of node hours. And this is, of course, not an optimal thing, because you want to solve this type of problems for, well, thousands or hundreds of thousands of parameter configurations, and not only a single parameter configuration. So why are these problems so difficult from a formal point of view? They suffer the curse of dimensionality. So that means, if you solve one of these optimization problems, or like, in one dimension, you would have this. But if you have like, say 10 optimization problems per dimension, but you have like 20 dimensions, like the one we have here, you have like 10 to the 20 problems you have to solve. So this is, of course, quickly infeasible. Then the other difficulty of this type of models is like the functions you try to approximate, like these optimal policies. They're highly nonlinear, so you need to have a tool that can approximate functions in a high-dimensional space that are nonlinear. And lastly, also, the models we try to approximate, the geometry is like highly irregular. So like it's very inefficient to map them to a grid. So I plotted down here on the right a simulation of such a model. So this looks like a, an ellipse. But so everything that is white here, the model would never reach these points in the state space. So now if you would map this type of models on a grid, and you have a 20-dimensional problem, most of the computation you would avoid. So what you want to have is a solution technique that can approximate high-dimensional policies on almost arbitrary geometries that are highly nonlinear. So how do we do that? We use, well, deep learning. Now, we don't use deep learning as it would be usually done in a supervised fashion. And why don't we do that? Solving these optimization problems is sort of, each individual problem is super costly. And so if we were to sample from this 20-dimensional state space, say solve 2 million optimization problems, then fit the neural net and do this recursively, this would be way too expensive. So what we essentially had to come up with is a way to train a neural net in a way where we can generate observations cheap on the fly. So the key ideas of these deep equilibrium nets is essentially we use the equilibrium conditions of our optimization problem as loss function, and then by simulation generate cheap data to train the neural net. So this may sound a bit obscure, but let me go just quickly back here. So in supervised learning, I would need to solve like millions of those, then fit the neural net against it, and do this repeatedly until convergence. In contrast, I don't want to solve these optimization problems. So I want to reformulate the economic model such that I just can essentially interpolate on a guess of a neural net. So how do we do that? We rewrite the optimization problem we had before in the first order conditions. So this gives a bunch of ugly equations. I'm not going into that. The important thing is you have a lot of these expressions that equal to 0. Then what I do is I take all these first order conditions as a loss function. I put them here. And now what I can do is I can just initialize my neural net. So the neural net will represent the optimal decision rules, the policies. So I simulate my model. So I take a guess of my policies. I simulate my model forward, say for 10,000 steps. This gives me training data. this comes at essentially zero, well, computational costs, because I just need to interpolate on a neural net. I know if I had the equilibrium policies, so the optimal policies, this expression G would hold strictly to zero. But of course, because I initialize my neural net randomly, this will be a huge loss function. Then I let the neural net with stochastic gradient descend to update my policies. I simulate again. My guess for the policies will become better, and I repeat that until convergence. So this simple algorithm, well, has all the necessary features that we just asked. It solves the model without the need of solving optimization problem. Due to the simulation-based approach, it only generates data where you need them. So like on this sphere. And lastly, neural nets, they're universal function approximators, so they can deal with nonlinearities in one go. So this works very well. But sometimes these models, they still can take too much time until they get solved. So we can then also parallelize this algorithm. And how do we do that? Essentially, one needs to be a bit careful with random seeds. But instead of simulating a 10,000 step simulation, we can break that up across n nodes, then do local simulations on each of the GPU nodes. Then we estimate a local gradient. Then we perform a ring order reduction, and then we update the gradient for the neural net, and we repeat this. So with this parallelization scheme for the small model, the relatively small models, we get excellent speed up to 512 GPU compute nodes on Pitt-Stained. This is the Swiss National Supercomputing Center's flagship system. And with that, we can now ask interesting questions. Some of the questions we want to know is like, how sensitive are integrated assessment models with respect to specific parametrizations? And this is of course very important, because as I mentioned before, this stochastic model that I have shown you before, people solve that for essentially one parameter configuration at a time. But for a policymaker, this is of course kind of useless, because you want to understand how sensitive your optimal policies are with respect to human components, right, etc., or how sensitive are they with respect to uncertainty in parametrizations that are due to climate change. So what we want to have now, based on solution tool, we want to build surrogate models and perform global uncertainty quantification. In particular, we tested in two types of uncertainty measures. One is the Sobol indices. So this is sort of, it's like a ANOVA decomposition. So you want to know how much of the uncertainty in the model is driven by which parameter. And also we want to know, or study univariate effects, meaning like we want to understand how policies, change over the computational domain with respect to certain parameters. And instead of solving the model now, tens of thousands of times that we want to avoid, we essentially start to build surrogate models. And surrogate models is essentially, we solve the integrated assessment model only once, but not only as a function of all its economic dimensions, but also parameters. Then we have a gigantic lookup table. And with this gigantic lookup table, we have then all the derived quantities of interest, such as the social cost of carbon as a function of parameters available. So just quickly mentioning what are these quantity? What are these uncertain? Well, these things. So Sobol indices is essentially, just to remind you. So if I want to know the social cost of carbon, it's an ANOVA decomposition, and the first order Sobol index would be essentially how much of the variance, of parameter I divided of the total system variance, while the univariate effects, they are essentially if you have, so Y would be the social cost of carbon. If you essentially integrate out all other parameters, how sensitive is a given policy with respect to particular parameter. Now, how do we do that? So, given our solution of our optimal policies, we essentially query in the domain for a variety of parameters. We compute the social cost of carbon. Then we fit the Gaussian process over those, and we don't just sample randomly because that would be inefficient, but we use Bayesian active learning to do so. So that means we start with, say, few points here and here in a domain. Then we know, so the red one would be the true function. That would be highly inaccurate. So based on Bayesian active learning, what would happen? So here, where the uncertainty is maximal, we inject an additional observation. So with very few observations, we get a surrogate of our quantities of interest that is derived from the model solution. Okay, so these are all the ingredients for this sort of generic solution frameworks we intend to build. Now, what can we do with that? So let me first show you how this works. So the simple model, we map it to a neural net, as I mentioned before. Here we have all the relevant dimensions. So capital, then you have here all the physics variables. Then you have here some stochasticity and the parameters. So this goes quickly to 20 dimensions, depending on the number of parameters we have. The optimal policies here would be capital, consumption, and mitigation. It's like of course, a stylized representation of the neural net. Then when we run this deep equilibrium net, you see that this thing converges very smoothly. Instead of like 100,000 node hours as our colleagues had before, it really solves in half an hour. So this is a big achievement, of course. And well, now with all the uncertain parameters that these models have, some of them are from the economics literature, finance literature, and here you have like a bunch of parameters, say for instance, like from the damage function, etc. That we know bounds on them, but we don't know how they look exactly. We stick them also to the model. And with that, we can now do, interesting predictions. So the first interesting prediction is, for instance, how does the social cost of carbon, which is a proxy to the optimal carbon tax, how should that, how will that change over time, subject, of course, to the underlying climate scenario? Now you see, at the moment, so our calibration starts in 2018, but like it's not so much different here. So like you see, the 50% quantile, so we are somewhere between $100 and $200, and this goes up over time. But in contrast to the previous literature, our tools can actually provide entire distributions. So the mean is not so much what is interesting. The interesting part of our computation tool is now we can really look at the entire distribution. So like if you look here at the 90s or the 99% quantile, you know, you really see there are unlikely scenarios, but like if they happen, like really shit hits the fan. So like, you know, if in a kind of okay scenario of climate, we reach $400, but like in a more unlikely scenario, things can become very costly. And so from a policy's perspective, you know, we're probably not so much interested in the mean, but rather how we can essentially truncate or like find policies that truncate the upper tail of the distribution of the social cost of carbon. So that's one thing that we can now do, or our tools enable researchers to do so. And as I said, so now in terms of uncertainty quantification, we can now also study which of the uncertain parameters drive the model outcome. So for instance, if you look at the social cost of carbon in this particular type of economic model, I wrote down, not surprisingly, most of the volatility of the model in the social cost of carbon is driven by the CO2 doubling temperature as a parameter. There is the second most dominant parameter is like in the, you know, from the damage functions, like the parameterization, you know, how much, if you have increasing temperature, you know, how much this affects the model outcome. And then there is some economic parameters that play, you know, the second important part. So here you would have essentially the discount factor, so how much you value consumption tomorrow over today, and some persistence in some economic stochastic processes. If you look at also the univariate effects, you know, here's the same picture. You know, we see how, you know, over the entire computational domain, social cost of carbon is sensitive with respect to certain parameters, while for others it doesn't. So this is also interesting in the sense, economists are often obsessed with calibration. But so this picture tells essentially, you know, like here this gamma, psi, psi, etc., or F 2x CO2 model is not driven, the model outcome is not driven by those parameters, so you don't have to worry too much about them when studying the social cost of carbon. Yes, so this is, of course, not only my work, but also of my PhD students and collaborations on the project too. We recently released the first open source package for this. And now, what can we do with that, or others can do with this? So moving forward, one can, of course, now start to study interesting things. So one is that is missing here is, for instance, regions. So like, as I started out this talk, we would like to study distributional effects, but this was not possible in stochastic frameworks just to computational limitations. Now with what we have built, this is possible. Other questions that are on the table are, for instance, the equilibrium climate sensitivity. This is an endogenous object from the climate science, and it's very hard to embed that in a dynamic stochastic economic models, but with Bayesian learning, we believe that is possible. So that's also a next step. Yes, and then of course, like when we go to regional models, we again, like we have limitations in terms of, you know, the simplified climate models we need to plug in. So also next step would be to embed pattern scaling into our solution framework. So there's a lot of things to be done, but you know, with this sort of project that we have here, we can now enable climate econ scientists to tackle questions that were out of reach recently. So I'm just in time. and well, leave the floor for a few questions. Thank you.
Thank you, Simon. Any questions from the audience? There's one. Let us know if you can't hear.
It's fine for now, thanks.
Oh, well, there is a question. Hello, can you hear us?
Hello? Yes?
Thank you. Very, very accessible talk to something very mathematical, so thank you for that. So in the physics literature or in the inverse problems literature, I've seen similar things with physics-induced neural networks, where they're sort of training a forward operator and an inverse operator at the same time within a loss function. So it's maybe a little bit similar to that. That's one part of my question, but if you could comment on that, then I'll go to the next part.
Yes, so can I, yes, so very good question. So like the loss or like the design of the neural net is in fact indeed what you would call, so like we would call it like a economics informed neural net, right? So you want to essentially use the expert knowledge to design a neural net. Well, you want to design the neural net such that it solves your problem optimally. So like the only tricky thing was essentially to think of a way to generate data, so to speak, to train a neural net that satisfies all the necessary economics efficiently. So that's one thing. So we had to essentially reformulate the problem slightly. But in the end of the day, what we're solving is recursively nonlinear sets of equations. So there's a bunch of literature. Well, I from the physics side, I know also like how you guys solve the PDEs. So it's sort of same type of inspiration. Does that sort of in a blurry way answers your question?
Yes, it does. It sort of makes it more relatable for me to ask the second part. So thanks for that. So you mentioned nonlinearities, which are hard because nonlinearities, can result in things like more than one path to a solution. And so, whereas when I think of a network, it's, you give it one input, you get one output. So how is, on the inverse side, how do you know which path is traversed?
That's an unfair question.
Oh, sorry.
It's a good question. No, so look, there's a few. So like, there's some models. They are convex. So there I know I will find a unique equilibrium. There's some models which you don't. So there may be multiple equilibria. And indeed, what this means is essentially you need to still solve. I mean, as you know, if you initialize a neural net, it depends essentially on a random seed, right? Also, where you start the simulations, is sensitive to your random seed. So that's, we need to solve essentially the model multiple times with different seeds. And, if you find the same or like roughly the same numerical answer, well, you claim numerical victory, so to speak. But, as these models are non-convex to some extent. So I have no guarantee that they converge to, to the same sort of solution if I run the model twice.
Right, but that's just life. So, but thank you very much for your answer.
Welcome.
Okay, I think we got to move on. Thank you very much, Simon.
Thank you for having me.